let us do one numerical to break that monotony of deriving, right. Okay, so now there is a system, right, there is currently, this is your example, so lambda is 100 packets per second, a system that is as a system arrival rate, and I have mu of 200 packets per second, right, this is one system. So this is an MM1 queue, this is one system that we are trying to. Our alternate system is I still have the same single queue setup, but with 100 packets per second as arrival, but now I have 2 servers, okay, and my mu is 100. So I have 2 slower servers and 1 faster server or 1 fast server, but only one common queue. So pictorially we have this, right, this is lambda, this is set, right, mu, well I should probably say mu dash, right, to differentiate these guys. Right. So this becomes your MM2 system. So now let us compute the the basic first order performance metrics, waiting time, delay, everything. So that you will compute and let me know. Compute all the 4, EFN, EFNQ, EFR, EFW. So MM2 requires one more extra computation, right. Okay, so bring out your trusty calculators and then tell me the answers. So that I just write down the answers, I am not going to compute them. You don't suppose you need a calculator for this. So EFR is 10, EFW is so don't forget your units as you go along, right. So EF 1 over mu is 5 milliseconds, so that is there, and EF did I get that correct? Is E of NQ that much? And E of N is 1, yeah, 10 into 100, okay, right. So waiting time is 5 milliseconds, response time is 10 milliseconds, okay, so fine, that was simple. Now for our MM2, so we will compute, so lambda equals, I am sorry, rho will be 0.5, will be same here. So mu dash is 100, rho is lambda by m mu dash, which is 0.5, m rho is 1. So I have given you a very simple calculation, m rho equals 1 should not be that much difficult, right. So P naught is 1 plus m rho by 1 factorial, so n 1 divided by, oh okay, but this is 1 factorial, 1 factorial, it is going from 1 to m minus 1, so it is simply m0 m rho by 1 factorial plus m rho to the m by 2 factorial, so 1 by 2 factorial into 1 minus 0.5, which is also 1. It's like how can't get any better than that. So 1 by 3, and this is simply this last term, right. Last term into P naught is your rho, that is all, you do not have to think of much. The third term into P naught is basically your probability of queuing. So that is also 33. So 0.5 33 divided by, this is also 0.33, okay, do not expect all queues to have the same value. Okay, so let us stop here for a minute, right. So expected number of E of n q, okay, let us compute E of w also, and then we will do something. So basically 1000 by 10, so 3.33. First one is better. Okay. So E of w is, yeah, so waiting time is 3.33 milliseconds here, and how much is on the other side was 5 milliseconds, right. So therefore definitely waiting time is less here, which is again intuitively okay, because you would expect that the two servers being there, right, at least I will be able to get one server faster, that is all. But if I look at the total response time, that is plus 1 over, but the dominant factor is 1 over mu, which is 10 milliseconds in this case. Previously it was 5 milliseconds, now it is 10 milliseconds. With only 100 packets per second, I will end up getting 10 milliseconds. So E of r is 13.33. So clearly that one is better, that is only got 10 milliseconds. And then E of n is 1.33. So what this says is having one faster server is better than having two slower servers, even though their combined capacity is the same. That is all it is trying to show. Okay. And if you want to look at that closed form expression for E of r, then this will become evident. So what you see is that this is the, I have not derived this, we can get this on the book itself, but what you see is your 1 over mu is the multiplicative factor, right. So for the one system 1 over mu is basically, even though m equals 1, mu was 200, other case m equals 2 but still your mu is 100. So this, unless, right, so and this is 1 plus some other smaller factor, right. So let us see how do we rationalize this. Yeah, so mu is definitely larger in the case of the first system, right, and unless this multiple tends to be larger in the case of MM1, right, this will not be there. So we will have to somehow prove that this rho by m, this PQ by m is going to be less in the case of MM1. Okay, that we will have to sit down and see if we can work it out. But in this example at least, right, the intuition is that faster the service time, right, your amount spent by the customer getting serviced is what everything is proportional to, your total response time, that is. So even the wait, so when you compare two systems, again the thing that you have to drive home is that simply do not compare waiting time alone, the total response time is what will make the difference. So we just compare one metric and then say I am done with it, right. If I ask you a question saying compare EFW and say which is better, which system is better, then you should not fall into the trap and say, well, that is not a good metric, you should say that is not adequate, I should also look at EFR and then say which one is actually going to be improvement. Okay, so that is one small example for MM2. Any questions before I move to the next derivation, next two derivations, depending on how fast we are.
This derivation becomes same. Erlang's formula which we calculated. Probability into number of total number of.
Oh, is it? Oh, so P of PQ into
So rho over 1 minus rho
is the number of, but rho number 1 minus rho is the number of customers in an MM1 system. Using that here also, but your EFN is not rho over 1 minus rho, is it?
No, if we compare with that.
Okay, okay, we will. Okay, I'll talk to you and see what now the derivation is there. Okay, so very quickly, how can we generalize this to a system where there is no queuing? So this is an MM, right. So there is no buffering, right. So the maximum number of customers, right. So the number of customers the system is less than or equal to the number of servers. So there are m, so m is the last parameter, by the way, is the number of maximum number of customers in the system. Okay, population size we went and figure out. So population size is the actual total possibility. Okay, so let us say this is the computer center example what they are giving. Your computer center has 100 seats, but the student population is 10,000, right. So you have this sort of, at a given point of only 100 customers can be in the system, but the total population of customers possible is 10,000. That is what the population size is, if you ever want to use that as a metric. Okay, so this is a system with no queuing, right. So in this kind of system, what will be the waiting time? Waiting time will be 0, because you come to the system, either there is a server free or not, or you simply leave the system, right. So therefore EFW is going to be 0 and EFR 1 over mu, right. This is going to be very fast derivation. E of n E of n is lambda by rho, m rho, or lambda by mu, m rho, right, and E of nq equals 0. So what is going to derive that in the system? What metric are we missing? The probability of call dropping, right, the probability of a customer arriving to the system and then not getting serviced, right, because you do not want customers to leave your system. If you go to a mobile shop to buy a cell phone, there are 4 counters that are servicing people, right, and every time you go they are all busy serving some other customer, you leave the system and go to some other shop to buy your cell phone, right. So therefore it is a big loss for this shop to have customers leave. So there is a penalty associated with call dropping. So we therefore derive this so called blocking probability. So that is the only metric that is of importance, because nothing else in the system is everything only depends upon lambda and mu, right. So blocking probability is what we want to define, right. So this is the probability of an arriving it will be dependent upon m. If I have more servers, I will have less dropping. Lambda is fixed. Assume that lambda is fixed and mu is fixed. M is what we have control over, right. So the service. No, this is not the population. M is the number of servers. That I just went back to your old question about population size. Here M is the number of servers in the system, and the final M is the number of customers also in the system.
In the system.
Yeah, this is MM1, like B is the buffer size, right.
Buffer size.
So there is no queuing in the system basically, right. So if I want to represent that system, it is a series of servers, right. So customers arrive and they simply go to one of these guys and then leave. This is rate lambda, this is mu, but there is no way for them to sit and wait. It is like making a cell phone call, right. You need one channel or a pair of channels to make uplink downlink calls, and when you arrive all channels are busy, you cannot be given a channel, right. We saw this in TDM also, because if we have 24 slots in a TDM frame, then all slots are used, you cannot be given any other slot. So you want to minimize, so the goal is to derive what is the best M, right. So this is very important for telephone networks. All this came about with designing telephone networks. What should be the number of this way back in the 1920s and 1900s and so on, where you need to decide some good value for M. How many circuits should I have in a system such that the customers do not get annoyed, right. So how do we derive that? So again, if you go back to our birth death process, it is very simple, right. I have either 0 customers, 1 customers, 2 customers. I do not go to infinity, I simply stop with M customers in the system. Everything else is the same, right. And so on. So only finite some number of states in the system, right. So what is P of n equal to? We derived this before, the same P of n that we saw for m equals to or n equals to m minus 1, right. So what was that? It is simply m rho to the n divided by n factorial. In the last experiment that we saw, we had m plus 1, m plus 2 was slightly different, but m and m plus 1, right, because if you look at m, there are m, right, sorry, 4, okay, right. So for m it is 1 to m, for m minus 1 it is and so on. So therefore my P naught is simply sigma n equals 0 to m and does rho less have to be less than 1 or anything like that? It does not matter, lambda can be as large as you want, it does not matter, right, because beyond m you are not going to grow, system size will not grow infinitely, it is a stable system whatever be the value of lambda, because you look at the summation there is, you can simply just a summation, right. So what you can plug in whatever value of rho that you want and you will get some answer at the end of it, you are looking at it as a simple summation, right. So this is the expression for P naught. So once I get this, what is the probability of a customer getting dropped or call getting dropped? Simply Pm, right. When the system is in state M, there will be no service for incoming customers because all servers are busy, therefore the connection incoming call will get dropped. So therefore blocking probability is X. So blocking will take place only when the system is in state M, right. So when I arrive to a system with m customers, I cannot be handled, I got to leave the system. So that is simply Pm, and that is nothing but and this is also attributed to Erlang, and what is this formula called as? It is Erlang's E, B, which one is this? E folks will know, which Erlang's formula? B. So usually the question is done the other way, so given lambda, given mu, what should be the m so that my target probability is less than say 0.5, 0.0001, usually keep that very low, like this 0.999999% should be the acceptance rate. So 10 to the power minus 7 for example is the call drop, 1 in a crore customers calls can get dropped. If that is what you are going to design for, you have to have that many customers, that many servers in the system, that is what you will use this formula for. Questions? So this, do you want to calculate? So here I don't, okay, let us try this. Right, so given lambda equals 10 packets per second, mu equals we will say 50 packets per second, right. And I only want 1 in 1000 calls to be dropped. So you can do a closed form solution, or that will be iterative, that will be iterative, or even binary search will do. You need some random large m and then keep halving it, or iterative, start from m equals 1, 2, so on and see where you finally hit.
That is close to this so that we can go more closer.
Well, I just start with m equals 2.
Plugin probability that is way off, and then we take so many iterations to get to.
Yeah, the number of iterations will be equal to the number of servers that you are looking for, right. That will be the worst case. Trying to reduce that, yeah, it is just a linear search, that is all, right.
We can do something
we
where
can do
we can
better,
estimate the close this thing, and then we can try.
And then but you need an initial guess, yeah, and then move in the one direction or the other, right. Yeah. But in this case, yeah, what would be the initial guess, right? Well, let us say m equals 2, right? What if m equals 2? What is the blocking probability for m equals 2? That you can find out, right? So what if m equals 2? So maybe we will get lucky here, right? So what is m equals 2? So we know that lambda by mu equals 0.2, right. So what is this going to be? This is going to be 0.2 squared by 2, no, m rho, so 0.4. Right. So m rho is 0.4, rho is or lambda by mu, right? Sorry, no, 0.1 will be 0.1. Okay, let us abandon this for now. So let us just do rho equals lambda by mu. So 0.1. So therefore blocking probabilities so that is easy enough to calculate. And what is that? 0.36, very high. Okay, that's, I am sorry, yeah, m rho is 0.1. Oh, sorry. Yeah, actually m rho does not matter. Oh, yeah, okay. We will abandon this all over again. Let us go to the next page. Yeah, actually m rho will never change because that is going to be fixed, right? Because the lambda by, no, yeah, you can
Get a good initial guess.
so m rho will be always lambda by mu, yeah, okay, sir.
You can actually put the denominator, which is going from n equal to 0 to m as from n equal to 0 to infinity, then it will become like e power m rho.
Okay, so you
Then you can get a guess for m,
okay,
and then start from that. We'll reach first.
okay, but you will get e power m rho, okay, yes, okay, but then your numerator then would be some you will have your denominator is going to be e of m rho, right. So something to the m rho to the m by m factorial into e of m rho equals this one, right. Then you can solve for m with that as an upper limit, right, and then try to lower limit, okay, and then start from there on. Okay. Yeah, that is right. As m increases, your m rho will be your rho will decrease, m rho will stay constant. Okay. So the 0.36 is correct for m equals 2. Okay, so when you come back on Friday, let me know what the answer for m is. Yeah. Yes, that's the other alternative that is suggested is to use approximate that denominator to have m row and then try to solve that to get a starting point so that you don't have to do this. But then if you have a computer, you just simply crunch it.
And like how much, like m equal to 5 also it is 0.0048.
0.0048. Okay, so at m equals to 6, then you should, or 6 or 8, you should be able to get it. So usually you try to guesstimate this, right? Because you never really know what the lambda is in a real system. But use that as an approximate measure. And then as you find the blocking probability is increasing, you simply add additional servers, right? If you look at today's systems, with the packet switch network, we always add additional servers if the delay goes up. In this case, you simply look at the, because you never know when a customer comes and does not get serviced in the system, right?